Okay, so let's talk about a few paradoxes, like the typical paradox of a car in the garage. Imagine you have a car like this one, and the car fits perfectly in the garage. That means you can close both doors very quickly, and the car is in there, no problem. No, the doors are open. So you move the car back some distance, and then you say, well, what happens if the car is and the garage are moving close to each other? The car is in there, and now we give it some velocity. Well, let's see. The guy in the garage, the guy that's standing here, he says, well, the car looks shorter because it's moving. So no problem, the car will fit in. And let's say we time the doors such that when the front of the car is in here, both doors close. Right? So from the guy in the garage perspective, everything is fine. No problem there. Now the car driver is a little worried because he sees the garage looks much shorter. And he knows we're going to close both doors at the moment his front is in here. So there's a problem in here. So who's right? The guy in the garage or the guy of the driver? You want to guess? Okay. So let's see. This is tricky because technically both sentences are right. The car will fit in the garage and will not fit in the garage. What is the definition of fit? This fits. Certainly this does. This does not. And what's the difference between these three cases? Say that again?
It's movement speed and between the reference.
What's the difference in here for the definition of fit is that in this case we have the doors closed. In this case, no. Right? You don't say that this fits because essentially you couldn't put the car with both doors closed. You say this fits because you could, right? So in the definition of fit, it's implicit the idea of simultaneity. It's implicit the idea of both doors closed. The car fits in the garage. We say that the car fits in the garage is if it is within the doors when both doors have been closed simultaneously. So fit requires the concept of simultaneity. And simultaneity, as we just saw, is a frame-dependent concept. So the fit that was mentioned by the driver is a different fit than that one mentioned by the guy in the garage. So with that in mind, let's see how both of them sees this event happening. So we do the same thing. What happens in this case? The guy is moving. At this point, we close the door. The door's very fast, and he keeps on moving. Right? Imagine it takes up nothing to close the door and open it. So in this case, it worked fine. Right? Both doors close simultaneously because the simultaneous was defined in this reference frame, not in the other one. How does the driver see the closing of the door? Now, we are now in the driver position, right? The reference frame is now in the driver's position. So don't expect the car to go over there, expect the garage to come here. So the garage is coming. At that point, this door is closed. And then the other door actually closes much later. So the car still passes through. Go ahead. Okay, but that's fine. So let's talk at last about the twin paradox, which you probably know very well. And it's not a particular twin paradox I like very much, to be honest. But anyway, it is. So you have two twins, Earl and Anna. Numbers, the names are properly chosen because Earl stays on Earth and Anna travels to Andromeda. So this is Earl on Earth and Anna is over there. And Andromeda is about 2 million light years away, far, far away. So Anna essentially reaches. Anna travels to Andromeda and comes back. Now she's traveling in a very specific way with a constant acceleration about the same we have right now, one G. So her spaceship is constantly accelerating. And the way we see it, the way Earl sees it, is because she's moving, she sees her clock going slower and slower. And of course, the more she accelerates, the more Earl sees her time going slower and slower. So she eventually reaches Andromeda, and because she's going so fast, she can reach Andromeda. It doesn't matter, it's 2 million light years. Her time is passing so slow that she could outlive that and actually reach Andromeda. Check out the beaches and come back. And then Anna reaches the Earth 80 years older than she left. So Anna went in here when she was born and came back 80 years older. But that time, Earth died 4 million years ago. That's the twin path. This is the explanation of what happens if you were actually able to do it. Now, people say, oh, this is a paradox. And you say, why? Because if the movement is relative, you can always say that Anna is staying and Earth is moving. So the movement is relative. So then, in that case, you would expect Anna to be dead and Earth to be alive. How can one be older than the other one? And the solution is simply that you cannot interpret Molly. Sorry, that was supposed to be Anna. That's an old slide. You cannot interpret Molly because Molly was moving. So you cannot interpret Molly, Anna at rest, and her moving away and back, simply because you can determine which is the one that went away. The movement is not really fully symmetric between the two, because Anna had to accelerate to come back. You know, I said that she was accelerating all the way back. That's fine, but even if she weren't, even if she wasn't with a constant uniform velocity all the way back, at the moment she needs to turn back, she has to accelerate, and that changes everything. Because when she accelerates, she can feel something. Earth, on the other hand, feels nothing. It's on Earth. So this is what we call the twin paradox or pseudo paradox, because it's not really a conflict of logics. One of the logics is actually wrong. And in fact, we have done this experiment in a very different way. We have put in one airport, we put 3 atomic clocks, 2 in a plane, and 1 staying in the airport, and then the 2 planes go all the way around the Earth and came back. And the time measurement of this atomic clock changed exactly by what was predicted by relativity. Now that's a hard experiment. It's not as simple as I put it in here because there's gravitational issues that we need to discuss as well. But that's all going to be part of the next part after the break.